Okay, so we're very happy to have Zack Sylvan, who will tell us about mirrors to points near SYZ singularities.
All right. Thank you. Thank you for inviting me for the talk, and thank you for the wonderful workshop. I hope in the future we have more with this format. I really like the introductory beginning. Yeah. Um, so the motivation for this, and I should say, this is not ultimately a talk about family Floer theory, and I'm not an expert in family Floer theory, but nonetheless, this is the motivation for what I'm going to get to. So I want to start by kind of giving an overview of what the point of family Floer theory is, what a point of family Floer theory is. Um, so the starting point is we're going to consider Lagrangian torus fibration. So it's going to be x over r base b. And I'm just going to draw this space that was supposed to be a straight line. No, there. There's my base. No, I don't want that. Okay. And here are a couple fibers. So I have one over, say, q, and one over q prime. Now, we have our space x. And one thing we might want to do is calculate the Floer theory of q prime in terms of the Floer theory of q. So I'm going to put some auxiliary Lagrangian L. And so say we want to calculate CF star of, so this is LQ and this is LQ prime. These are Lagrangian tori. L with LQ in terms of Floer cochains of L with LQ prime. That's a thing we might want to do. And I guess we should allow ourselves this vector q prime minus q, which is this is some class, and remember for a torus fibration, the base is identified with h1 of the Lagrangian. This is something in LQ, h1 of LQ. In this case, just with our coefficients. Okay, so let's try it. In this case, we have two intersection points, x and y. So CF upper star of L with LQ. We have some copy of the Novikov field associated to x. We have one associated to y. And we have a map. Let's maybe, no, let's, no, fine. We have this region. This is a bygone. This contributes to the Floer differential. And the area of this I'm just going to say is A. So we have a differential which is just multiplication by t to the A. Maybe, as is traditional, I should recall what this Novikov field is. So recall not A, lambda. I guess I should say recall the Novikov. Maybe, can I do this? Novikov field lambda is kind of formal power series with real exponents. sum of AI t to the, what am I calling these? VI, where AI is in some ground field. I'm going to just work over C, but you could work over something else. And VI are an R, and they go to infinity. Okay, there's our Novikov field. Going back to the computation, so this is the Floer cochains of L with LQ. What if we wanted CF upper star of L with LQ prime? Well, we'd have lambda x prime, that's over here. Here's x prime. It's going to go to lambda y prime. Here's y prime. And now the differential is multiplication by something smaller. It's by this smaller area B, right? So the differential is multiplication by t to the b. Now we have, some canonical identification of these things and some canonical identification of these things, which just come from, they're both rank 1 free modules over lambda, and one is just associated to x and one to x prime, and we have this path, so we can treat them as the same thing. In the background, this identification might, involve some kind of non-trivial valuation if the red lines were tilted, but that doesn't matter. Okay, but as stated, the bigger issue is we just don't have enough information. Oops. Have enough information. Why not? Well, the number b cannot be extracted from the numbers a and this cohomology class q prime minus q. Right? B is just some essentially arbitrary number, and if we want to recover it, we need to keep track of something else. So what's the missing data? Kind of fundamentally, it's the holomorphic disk, right? The holomorphic disk. Let's actually highlight this. Oops. We have this disk here. This is, let's actually just do that. That's our disk U, holomorphic disk U. And so if what we need is some way to keep track of the extra information about U that was forgotten if all we kept track of was its area. So we know this A, that's the energy of the disk. So what's left is its homotopy class, which under assumptions that I'm going to make in the background are just encoded by the boundary. So what's left is the boundary of U. Actually, let's write that over here. What's left is boundary of U. And this is, in some path space from X to Y. This is paths in LQ. So what we're missing is this boundary. The boundary on L is, in this case, less important. Okay, so once we have that, now B is A minus, well, something I get by taking this path, transporting it in this direction, and calculating this area. So I can write that as Q minus Q prime paired with boundary of view. Now this is some sort of flux pairing. And maybe I should note really we need to do something if we want to pair a cohomology class with a cochain. Pair Q minus prime minus Q with a path, but it doesn't really matter how you do it. The result. Okay. So let me reinterpret this now. So put differently, we can treat this boundary of view as a function. Boundary of view as a function. On this cohomology group, H upper 1 of LQ. And I'm going to actually do this with lambda star. So I'm no longer going to view Q minus Q prime as some real cohomology class. I'm going to exponentiate that, or rather I'm going to take T to that power. And that way, the correction, T to the B minus A, that's the correction to the area that we need if we want to calculate the Floer differential for LQ prime instead of LQ. So this correction comes from evaluating the function, it on, I'll just write it as T to the Q prime minus Q. I guess really that's like there's some product, right? And something like that. Okay. So what's the outcome of all of this? So the first thing is that the coefficient of the Floer differential so let's write that. Boundary of X is some sum over disks of T to the area of the disk, or I guess I should write that as energy, times boundary of the disk, or again, pairing with the boundary of disk, perhaps, times y. So this is the coefficient. This is a function. A function on a piece of this H1 of LQ with lambda star coefficients. That's the first thing that we got out of this. The second thing that we get out of this is if we look at this H1, LQ lambda star is a non-Archimedean thickening of well, I'll say of the dual torus. The dual torus being H1 of LQ S1, and this is just under the inclusions. S1 goes into C star, goes into U lambda. I'm going to write, I'll say what that is in a second, goes into lambda star. U lambda is what's called the unitary group for lambda, which is just the kind of the elements of valuation 0. So the things where the kind of the leading term is a t to the 0. So when we do this, we're no longer thinking of these non-Hamiltonian deformations as kind of being associated to non-unitary complex numbers. We're thinking of them as being associated to non-unitary elements of the Novikov field. So there's a third thing that we get out of this, which is that 1 and 2 imply, how do I want to say this? Well, the coefficients of the differential are locally given by, or by functions on the mirror. Now, that's a local characterization of them. What's a global characterization of them? That's a theorem, or a combination of theorems due to Fukaya and due to Abouzaid, that says that, in fact, they're module maps. And the assignment L goes to CF upper star of, I wrote it the other way, but this time I'm going to switch, I guess, because otherwise it's not covariant. Well, depends on your variance, I guess. I'm just going to write it this way. We can switch it if you want. So L maps to Floer cochains, where I vary the fiber, defines, well, I'll say sends L to the sheaf homologically mirror to L. To L. Okay. So I guess I'll list some caveats and then pause for questions. So the first caveat of this is that we assume that there aren't any kind of bad holomorphic curves. So it assumes that LQ, or that the LQ, the fibers they bound no disks, and X has no spheres. Otherwise, you end up having trouble matching things up as easily. That's not surprising. Floer theory is usually easier when there's no spheres and disks. 2 is that this doesn't provide guidance on the reconstruction problem. In a sense, it's saying, well, we know that the mirror torus is mirror, and here's how we can exhibit homological mirror symmetry using that knowledge. And there's a third caveat, which is kind of the big one from the perspective of this talk, which is that it doesn't, well, not it doesn't, but it's that, whoops, is that it's unclear how to deal with singular fibrations. And what I mean by that is very simply that if you have a singular SYZ fibration, then you have singular Lagrangians floating around, these singular torus fibers, living in codimension 2 families. And if we have immersed singular Lagrangians, we have tools to deal with that, but we don't really have tools to deal with non-immersed Lagrangians. So my goal this talk is just to explain Mohammed and my approach to 3. So explain our approach to 3. Okay. Any questions?
Zach, is this the breakpoint in your talk?
It can be, but it doesn't have to be. Like, I'll get another breakpoint in like 3 or 4 slides.
Okay, yeah, no problem. It's still early, so yeah.
Yeah, either way. Oh, sorry. Was I muted? I was muted. Sorry. So yeah, this doesn't have to be the breakpoint. Maybe you could hear me. I don't know what's going on.
I could hear you. No worries. That
Okay.
sounds good. We can wait till the next.
I'll keep going for a little bit. Okay. So kind of the input to this, again, as I said, this doesn't provide guidance for reconstruction. So kind of we ask the experts in this conference kind of what are some of the kind of local models for singularities. And what I've been told is that kind of the big examples, and all of these examples we've seen, all of the kind of main singularities we've seen fall into this. I don't know if this is all of them. I would love for someone to tell me, is this kind of after deformation all of the singularities? But the kind of the singularities that we end up dealing with are these affine varieties, product of xi, product from, that's nonsense, xi, I go from 0 to m, so these are the C, these are in C, equals 1 plus sum j equals 1 to n of yj. So these are the local models for these singularities. And our goal is just going to be to establish mirror symmetry for the, well, homological mirror symmetry for this in a way compatible with family Floer theory. Concretely, this means we need to put kind of mirrors, or I should say points on smooth mirror tori on the same footing as points on singular mirrors. Mirror fibers, I'll say. Okay. In particular, we'd better be able to cook up point-like objects. We want a closed torus-like Lagrangian brane, closed and torus-like for each point on the mirror. Right? In the smooth case, we had our Lagrangian torus fibers, and any of these local systems that we equipped it with gave us a torus-like object. That changing the local system, even if it's a non-unitary local system, doesn't change the self-Floer homology of these tori. So in the smooth case, we had all of the kind of mirror points that we could want. So our goal is to do the same kind of thing in the singular case. So let me just do a few examples of what are these model spaces, model singularities. So x0n, well, is given by x0 equals 1 plus y1 plus up to yn. And this is isomorphic to c star to the n with the y coordinates. X0 is allowed to be anything, and it can, in fact, be anything. If we did x and 0, we would get x0 up through xn equals 1 plus, equals just 1. There's no y0. And so this is isomorphic to c star to the n with coordinates, x1 up through xn. Right? We can solve for x0 and use the others as the coordinates. And we know c star to the n is indeed mirrored to c star to the n. If we do this with x11, we're going to get x0, x1 equals 1 plus y. And this 1 plus y just tells us that y can be anything except 0. So this is equivalent to just x0, x1 is not equal to 1. So this is c star, no, not c star, c squared minus a conic. This is the focus-focus singularity. Okay. I think I'm going to be the person who says least about the focus-focus singularity in this conference. But that's one of the examples. I mean, we already know mirror symmetry for this. And there's only one singular Lagrangian, and it's immersed. And so, in fact, we can completely understand it, all of the points, using just just immersed Lagrangian Floer theory in the standard way. So now x12, whoops. So that's x0, x1 equals 1 plus y1 plus y2. I'm not going to fully describe this, but I'm going to observe that it has two obvious C star cubed charts, and they're given by x0 is non-zero and x1 is non-zero. What does the mirror look like? We have x21 so this is x0, x1, x2 equals 1 plus y1. This has a fibration called just 1 plus y1 to C, or to a disk. It has a singular fiber over 0, right? When x0, x1, x2 is 0, that's the discriminant locus. And it has a missing fiber over 1. Y1 is not allowed to be 0, so 1 plus y1 is not allowed to be 1. This situation, just like in x11, has kind of natural Clifford and Chekhanov tori. So here's my Chekhanov torus, and here is my Clifford torus. And we should imagine that these tori are on the right are mirror to the C star cubed charts on the left. We could go into a longer story about kind of there being 3 ways of kind of connecting these tori to one another, but I'm going to move on and just talk about what the general story is, which is that we have m+1 of these C star to the m+n charts, one for each x that we choose to that we allow exclusively to be 0, but they don't cover the entire space, right? There are situations where we have more than one x which is 0, and that's fine. That's in fact precisely the locus where this projection is singular. To get around this, we either need to figure out how to do Floer theory with non-immersed Lagrangians, or we need to find a replacement. And maybe I should just say finally why I'm saying that, which is that the missing points we somehow expect to come from this kind of gray circle that passes through the singular point. But this is not immersed. This has the kind of singularity of this Lagrangian looks like a cone over 2 tori. So either we have to do Floer theory with that Lagrangian, or we need to replace it. And I think this is a reasonable point to pause.
Okay, thanks, Zach. Any questions for Zach on the record? Okay, what I'll do is I'll, was there a question? Sorry. Kenji, if you're speaking, I think you're muted. I don't.
Yeah. Can you hear me?
Yes.
Okay, so if you consider this regular fiber, which converges to singular fiber, and you consider the structure of abelian group of the regular fiber, that's a limit and a singular fiber outside of the singularity?
What do you mean? Oh, like, is there, sorry, you're taking a kind of family of objects supported on smooth fibers and you're having them
Yes.
degenerate?
And you know, this regular fiber is a toroid, so it has a structure of abelian group.
Yeah.
And in certain cases, this limit is something like a non-compact abelian bright, I mean, non-compact abelian group if you remove the singularity. And my question is that kind of phenomenon happens in your particular singular fiber or not?
I don't know. Yeah, we haven't thought about kind of, and somehow your question is asking whether we can like whether we're going to be able to like geometrically add together sections even over the singular locus.
Yes, that's right.
I don't know. We haven't thought about that.
Okay, yeah, thank you.
Sorry.
Okay, perhaps what I'll do is I'll pause the recording and we'll move to sort of unofficial discussion for 5 to 10 minutes in that range.
All right. So I guess I'll talk at this point about our strategy for dealing with these singular fibers. So step one is going to be to produce an immersed Lagrangian, right? That's what we know how to do Floer theory with. Produce. LMN in X MN, together with kind of a good space of deformations. With a space def geo, we've decided to call them geometric deformations of deformation cochains. Okay, and then two, we're going to identify the space of non-zero objects with, I don't want to say the points on, I should say of this deformation space. With points on the mirror. And so I should say we need to be able to figure out which points of def geo correspond to which points on the mirror. We need to be able to determine, specify which points of def geo give which points on the mirror. Right, we don't just want, to know that def geo is abstractly isomorphic, but we're going to want eventually to kind of be able to say what the isomorphism is and use that kind of to kind of glue this in as a chart for the mirror so that we can test a arbitrary Lagrangian and do family Floer theory. So what we're going to need for this is a mirror to the structure sheaf. To O. Okay. So I'm just going to say kind of a bit about step 2, how we kind of produce this mirror to the structure sheaf, and kind of what it's going to let us do, and then I'll spend the rest of the time on step 1. So our starting point is we have a standard projection, which is xmn maps to C by 1 plus the sum of the y's, yj. And if I draw this, as I mentioned, or as we saw before, this has 2 special fibers. There's a special fiber at 0, and there's a special fiber at 1. So I'll start with the general fiber. So the general fiber is, if I pick some arbitrary point, that's C, whoops, then that means the product of the sum of the y's is the same as the product of the x's. So that means that the product of the x's is not 0. That means I get a C star to the m coming from the x's cross. If I take the sum of the y's and that's something non-zero, then I get a pair of pants. H n minus 1 coming from the y's, where here H n minus 1 is the pair of pants. Sum of yj equals, am I giving something? I guess equal. I think 1 plus the, I think I'm supposed to be writing it this way. 1 plus sum of yj equals 0. That's my pair of pants. General fiber, the x's give us C star to the n to the m, and the y's give us a pair of pants. So at 0 we have a singular fiber. At 0, and that looks like, well, the product of the x's equals 0. There's also a pair of pants floating around, but the kind of this family is trivial, or is trivializable for the y's near 0. So I'm just focusing on the type of singularity, which is product of xi equals 0. I guess I could say cross H n minus 1. And at 1, it's not a singular fiber. This projection is smooth at 1, but there is essentially a singularity at infinity. So a special fiber at 1, and that says that, and that's modeled on, C star to the m cross, and now, well, it's cross sum of yj equals 0. So the sum of yj equals 0 looks like a C star times a lower dimensional pair of pants. Now our Lagrangian, and I'm going to call it O sub mn as a hint that it's going to be mirror to the structure sheaf, is r plus to the m plus n. So this has coordinates x1 up through xm, y0, or not y0, also y1, yn. Yeah. And what this looks like is it just comes out over here. It fibers over this arc. And it's a disk. Okay. So the theorem, if we look at this disk, is that it is mirrored to the structure sheaf. So that says that there is an equivalence of DG categories twa pi of the wrapped Fukaya category of X M(n). This is ultimately just an affine variety. It makes sense to talk about its wrapped Fukaya category. And that's equivalent to, I'm just going to write co, but I mean the DG version of X N M. And this sends O M N to O. I should also point out that these are all smooth. And so co and perf are the same. Okay, so what this means that we can identify points of Lagrangians mirror to points by kind of identifying them, or I guess, yeah, in spec of CF0 of, I guess I could write HF0, sure. HW, this is wrapped of OMN. And by open-closed mirror symmetry, this is the same thing as spec of SH0 of XMN. You can see kind of it ties a little bit into what Yoel talked about, but kind of the closed open map just gives us an equivalence, canonical isomorphism between these creatures. Okay, that's all I'm going to say about wrapped homological mirror symmetry. So at this point, if there aren't questions, I'll continue to discussing mirrors to points, and so closed Lagrangians.
May I ask questions?
Yeah, of course.
So you write spec, right? So it's a scheme, not so it's not a rigid space, but a scheme.
Yeah. So we're doing this just as we're doing this just as like complex varieties. Kind of the computation. What if you put in areas would give us this essentially the same equation, the correct formula over the Novikov field, but kind of for simplicity, kind of we're and because this is still how we end up wanting to identify kind of this is how we want to construct isomorphisms in the wrapped category, or this is how we want to construct isomorphisms of these torus-like Lagrangians. So,
okay, yeah.
So basically, this is good enough to kind of figure out which torus-like Lagrangians are isomorphic to kind of which genuine torus fibers, and then kind of we can enhance everything to the non-Archimedean setting.
Okay.
So the starting point is again this projection. So we have, I'm going to write it again, XMN maps to C. And this, I'm going to give this a new name, rho n. And so this is 1 plus the sum of yj. Right? So let me draw a picture of this. So again, we have kind of this special fiber. We have a thing. Maybe I'm going to move these closer together, actually. A special fiber and a thing. And remember that the kind of singular Lagrangian that we want philosophically, whoops, that's supposed to be a different color. The singular Lagrangian that we want philosophically looks like this. And and again, philosophically, LMN lives over a cable of the the obvious singular circle. I can't write. So let me draw what that's going to be. It's going to, in fact, just be Seidel's Lagrangian. Maybe I can draw a little bit better. So I'm going to give this thing a name. This we're going to call L1. This is kind of the standard one-dimensional Lagrangian. Okay, so what we need to figure out is what to put in the fiber. Okay, so there are two kind of options. So the kind of obvious solution is to say, well, the fiber is C star to the M cross H n minus 1. So let's use Tm cross, I'm going to say S, I can't call it S, I'll call it, L n minus 1. And so this is going to be Sheridan's Lagrangian, which kind of lives in the center of the pair of pants. So this probably works. But we found it just a bit tricky to compute. Compute stuff in XMN. Okay, so what was our approach? We cooked up additional projections to reduce everything to curves in C. Oof. I can't seem to, there we go, okay. So let me say what that looks like. So I called this row n because it's the nth projection in a whole family. So row 1 is just 1 plus y1 over y2. And I should mention this is the same thing as y1 plus y2 over y2. Row 2 is 1 plus y1 plus y2 over y3. And so, of course, that's just y1 plus y2 plus y3 over y3. And so we keep writing all of these. Row n is 1 plus y1 plus up to yn. And what are we dividing by? Well, we're dividing by 1, but I'm going to pretend that that's like yn plus 1 equals 1. Okay, and I want to notice something about this. The divisor, I'm going to call this di, which I can define to be rho I inverse of 1. So this is the fiber over 1 for rho I, which is, if we look back, for rho n, this looks like the special fiber, which was not singular. This is a general thing which happens. The rho I inverse of 1 is, well, so this is, if rho I equals 1, then this is saying 1 plus, not 1 plus, just y1 plus up through yi equals 0. And that's the same thing as rho I minus 1 inverse of 0. Right? If I did this with row 2, then row 2 inverse of 1, that's saying y1 plus y2 is 0. So that's saying that row 1 is 0. And so this inspires defining di plus 1, or not di, dn plus 1, the last one. So that's rho n inverse of 0. And so that's just the set product of the xi equals 0. So that's the singular locus. Okay. This is the kind of key geometric kind of trick, is having all of these projections. So what do they do? Well, they define a complete set of coordinates once you take the x's, right? So here we have one row for each y. And then if you take x1 through xn, or x1 through xm, then you have kind of one x for each additional dimension. And so this is the correct number of coordinates. And the fact that, and the kind of nice fact is that once you remove all of these divisors, then these define the splitting of the complement, right? So now we can define L mn to be, well, in the x coordinates, I just take a torus, Tm. This is in the xi coordinates, cross L1 to the n minus 1, or not to the n minus 1, just to the n. And so this is in the row I, or row j coordinates. Okay, that's the Lagrangian. So what's the difference between this and what we would do with the kind of the obvious solution? In the obvious solution, we still have this torus, but we have a single Lagrangian in the pair of pants fiber, along with an L1 in the base. So our additional projections let us break that down and just put a bunch of L1s instead of one L1 and one Ln minus 1. And so now the deformation space is def geo is, well, H1 of Tm plus, I'm just going to say the degree 1 self-intersections. Of the various L1s. Now, each L1 has 2 degree 1 self-intersections. Those are, doing this in blue, those are here and here. This third self-intersection has degree 2 or degree minus 1, depending on which one you look at, but it does not have degree 1. So this is, so there are 2n of these, or yeah, 2n. There are more generators than we might want. But nonetheless, a theorem is that the variety of non-zero objects, beta in def geo, where HF of L, M, N with that deformation is non-zero, is isomorphic to X, N, M. So in other words, the non-zero deformations, or in other words, the branes that we define, the non-zero branes that we define on LM when we restrict to this space is the same as the mirror. It sounds like that wasn't quite aimed at me. Okay, so I'm going to just at this point use my remaining few minutes to talk about how do we do this kind of computation, because kind of from my point of view, the big benefit of this Lagrangian is how easy it is to compute with. And so the key fact is that holomorphic curves in XMN are precisely kind of tuples of curves. So one for each coordinate. With simultaneous incidence conditions. In other words, so let me do an example. Let's say we want to find some disk which is non-trivial in row J. So maybe we look at this thing. Whoops, wrong button. Still the wrong button. Highlighter, please. So here is kind of one disk that, oh, actually, just for magic's sake, I'm going to put this in the bottom. It doesn't actually matter. Actually, no, it, oh, sorry, I'm just completely drawing the wrong disk. That's the bigger issue. The disk I want to draw is this one. Oops. So I want to look at this disk. In the base, this is a disk with kind of one blue corner and no other corners a priori. And it passes through this divisor DJ. And so in the fiber, I need to draw some disk that passes through the divisor dj. And it turns out that there's a unique, I mean, up to like, rotating the parameterization, there's a unique disk that has like the kind of top component in row j minus 1 and the bottom component in row j. What kind of disk is this? Well, there's like a blue dot over here, which I'm going to think of it as an input. I'm going to think of this as a disk that would contribute to curvature. So this blue dot is an input. That's like having, a unit over on the top. So there's, some like blue unit at the top. And we have an output of the red thing. The red thing is where the curvature is supposed to live. And so I need an output somewhere at the bottom. And whoops, I should make this red. And if I want my output to be the unit at the bottom, then that lives in a fixed position. I don't get to move where the input is. So this, in fact, is a rigid disk contributing to the curvature. There's a second rigid disk that cancels it. Whoops, I want to be here. So there's a canceling rigid disk, which says, well, at the top, the unit was an input. So I could have instead, drawn this thing, and that would still count just fine. And it would be the same disk at the bottom. This is two disks out of many that contribute to the curvature. These two cancel. All of the others also cancel in pairs. If I can take one more minute, I think I started 2 minutes after.
Oh yeah, sure, go ahead.
So I can just indicate what happens with row n, right? So if you have something that passes through any of these divisors, D1 up through Dn, then kind of it's going to look like these kinds of pairs of disks. In row n, if you have something passing through Dn plus 1, that's this kind of singular fiber. And again, at the bottom, we could have something like this. Now kind of somehow row n is really playing the role of the thing that was the fiber before, that was the row j minus 1. Somehow this comes, these x's come next. So we could have this kind of disk that passes through Dn plus 1. And in the x coordinates, well, this disk intersects Dn plus 1 once. So it's not a matter of, drawing something that passes through this singular point. Right, there's some singular point, but that's not where these disks go. These disks pass through some smooth point of that thing. They pass through one of the coordinate hyperplanes where just one of the xi's becomes 0. So there's one up there. There's another one down here. So there's one for each I equals 1 to m, and then there's also one which is constant. And kind of this is one more constant in each xi and non-constant in x0. So this is all the disks. So this is how you would compute the curvature. The curvature vanishes. This is also how you would compute Floer theory, the differential. You could try to compute the infinity operations, but it starts to get complicated. But no matter what you're doing, you can just explicitly see what the disks are in each of these projections. I find that really convenient. Anyway, I'll stop at this point.
Okay, thanks very much, Zach, for your talk. Are there any questions for Zach on the record? I have one, actually, Zach. I was just wondering, I missed this bit a little bit, but so in the deformation space, so the deformation space is like some, you said it's like something like C star to the M cross like C to the 2n or something. So is the point here you see some equation? It's not exactly the defining equation for x n m, but it's something isomorphic. Is this deformation space a little bigger dimensional than the?
It's much bigger dimensional. So
Yep.
you get
Okay.
a bunch of equations. Essentially, for each of these pairs, rho j minus 1, you're going to get an equation. And together, those conspire to give you the thing you expect. So the j's give you this product of the x's. So what you're really seeing is you have two variables, like one for the first blue dot, one for the second blue dot, and you get an equation about their product that relates it to kind of something one level down. And these combine to give you the product of these mirror x's. You can't see where I'm indicating. But I was looking at the left here. And then on the right, we have kind of exactly n+1 disks, and those just add together. And that's what ends up giving you the equation that looks like 1 plus the sum of the y's.
Okay, thanks for the clarification. Other questions for Zack on the record?
Can I also ask a question? Yeah, so are there embeddings of models with low dimensions cross like products of each other to, let's say, a given model? Like XMN, I think like there's some embeddings maybe of C star to the M+1 or something like M+N, something like that. And
sure. Yeah, I think
do you compute restriction maps, for example, in your first approach? Like Viterbo restriction maps?
Sorry, which first approach?
Like the first theorem that we had with the wrapped Floer theory.
Oh, no. So this wrapped Floer theory. So no, we don't compute any kind of maps between these different XMNs. All right, I guess, except for like very degenerate values of M and N. What we do over here is we just kind of cut this in half, and we use a Cauchy property.
Okay. Yeah, I mean, I don't know what embeds in what anyways. I was just asking.
I mean, I do think there are some kind of interesting maps between these.
Yeah.
In a sense, kind of, it comes from these projections and just kind of forgetting some of them. I think that will give you maps between these.
Okay. But you didn't really try to systematically analyze.
We didn't try to systematically analyze that. No.
Mm-hmm.
We spent a long time looking at stuff like that, where we thought maybe we would get, an XMN-1 in the fiber after changing some divisor. And I think that's true. But at some point we realized that we could just write down all of these projections and the picture got a lot easier.
Okay, thank you.
Other questions? Okay, so what I think we'll do now is we'll stop the recording and then move to further informal off-the-record Q&A.